Okay, hello everyone. So in this video, I'm going to show you how to find the integral of rational fractions of the form p of x over q of x by applying the partial fraction. Okay, so say we want to find the integral of x squared plus 2x minus 2 all over x cubed minus 4x dx. So what we gonna think of is a straightforward formula to find the integral of this fraction. So since we cannot easily identify a straightforward formula, what we're going to do is to find fractions that when added is equal to the given functions. Okay. And in this case, I have investigated that this fraction is equal to 1/2 all over x plus negative 1/4 over x plus 2 plus 3/4 all over x minus 2. When added, when these three fractions are added, then the result is x squared plus 2x minus 2 all over x cubed minus 4x. So which means that can give us an easily way on how to find the integral of x squared plus 2x minus 2 all over x cubed minus 4x dx, and that is just equal to the integral of 1/2 over x plus negative 1/4 over x plus 2 plus 3/4 over x minus 2 dx, and this can be written as a sum of the integrals of 1/2 integral of dx over x minus 1/4 integral of dx over x plus 2 plus 3/4 integral of dx over x minus 2, and this give us a hint that an integral of d over u will lead us to an ln functions. Particularly, we have 1/2 integral of dx over x is equal to 1/2 ln x minus 1/4 integral of dx over x plus 2 is negative 1/4 ln x plus 2 plus 3/4 the integral of dx over x minus 2 is equal to 3/4 ln x minus 2, and then you can now add c. So that means the integral of x squared plus 2x minus 2 all over x cubed minus 4x dx is equal to 1/2 ln x minus 1/4 ln x plus 2 plus 3/4 ln x minus 2 plus c. The question now is, how can we easily identify this sum of fractions? And this sum of fractions is what we call a partial fractions. Okay? And in this video, I'm going to show you how to find that partial fraction, and the process is called partial fraction decomposition. Okay, and a partial fraction decomposition is a reverse process of addition of fractions. Say we shall now consider an integrals involving rational fractions, that is fractions whose numerator and denominator contains polynomial in terms of the variable of integrations, say p of x over q of x. And if the degree of p of x is greater than or equal to the degree of q of x, then the fraction is said to be improper fractions, and that can be reduced by a long method of divisions. Okay, and dividing p of x over q of x, the result would be a mixed fraction consisting of a polynomial and a proper fractions. And assuming all fractions considered are irreducible, and then we can now apply the process of partial fractions, or the process of partial fraction decomposition before integrating. But we have to remember three things, okay? Number one, so the fraction should be proper. That is, the degree of the numerator is less than the degree of the denominator. Number two, the fraction is said to be irreducible. That is, both the numerator and denominator do not have common factor or factors. And number three, denominator should be factored out completely. Okay. Say we consider this theorem. Any proper fraction can be decomposed into a sum of partial fractions subject to the following classification. Case number one, the non-repeated linear factors. If a linear factor ax plus b appears once as factor of the denominator, then we associate a partial fraction equal to this, equal to capital A all over ax plus b. Okay, and for case number two, the repeated linear factors, if this linear factor ax plus b appears n times as factor of the denominator, and then we associate a partial fraction equal to this. Okay, that's a1 all over ax plus b plus a2 all over ax plus b squared, running until a sub n all over ax plus b raised to the n power. And case number three, the non-repeated quadratic factor. So this time, the denominator contains ax squared plus bx plus c as one of its factors, and that appears once. So we associate a partial fraction equal to this, capital AX plus B all over AX squared plus BX plus C. And finally, for case number 4, we considered repeated quadratic factors. That is when this quadratic factor, AX squared plus BX plus C, appears n times as a factor of the denominator, then we associate a partial fraction equal to this. Okay. So the only thing we need to consider are the factors of the denominator. Going back with our example, so this time, I will show you how to decompose x squared plus 2x minus 2 all over x cubed minus 4x. And then the first thing we need to do is to factor out the denominator completely. And x cubed minus 4x can be factored out as x times x plus 2 times x minus 2. So we take note of the factors of the denominator. One is x plus 2, and the other one is x minus 2, which are all linear factors. So this will fall on x is repeated once, x plus 2 is repeated once, and x minus 2 is also repeated once. So this type of fraction is classified under case number 1 for non-repeated linear factor. Okay, so for the first linear factor ax, we associate a partial fraction equal to capital A all over x. And then for the second linear factor x plus 2, we associate a partial fraction equal to b over x plus 2. And then for the third linear factor, x minus 2, we associate a partial fraction equal to c all over x minus 2. Okay? So how can we easily identify whether the partial fraction is correct? So you take note of the degree of the denominator, which is equal to 3, and that determines the number of variables we are going to look for. That's A, B, C. So we have 3 variables that we need to look for. And how many terms do we have? That's the number of factors. We have 1, 2, and 3. So we have 1, 2, 3 terms. Okay. So the next thing we need to do is to look for the values of A, B, and C. And that can be done if we're going to write the right side of the equation as one fraction by getting the LCD. That's x times x plus 2x minus 2. Okay, so we have the least common denominator divided by x times a. We have this expression plus the LCD divided by x plus 2. The remaining term would be x minus 2 times b plus the LCD divided by x minus 2. The remaining term would be x and x plus 2. So we have c times x plus 2. And what we notice is that the denominators are equal. So we can now drop it off, and that leads us to this equation. Okay, so that is the same thing as when we multiply both side of the numerator by the LCD x plus 2 x minus 2. Okay, and then to solve for the values of a, b, c, we can use the Heaviside cover-up method. In Heaviside cover-up method, so we think of values of x such that the denominator will vanish, such that the denominator x will become 0. X plus 2 will become 0, and x minus 2 will become 0. So that the method is called the Heaviside cover-up method. Okay. So for x, we let x equal 0. For x plus 2, we let it be 0, so x equals negative 2. And then for x minus 2, we let it to be 0, so x equals 2. So you notice that when this becomes 0, we can look for the value of a. When this becomes 0, we can look for the value of b. And when x minus 2 becomes 0, we can solve for the value of c. Okay, we remember this. X equals 0, x minus 2, and x equals 2. All right, so again, so if x equals 0, what we only need to do is to replace all x here by 0. So we have this equation. And you notice that since this is 0, this is also 0, then this term will become 0, and also this term will become 0, leading us with this is 0, this is also 0, negative 2 on the left side, and you just multiply this 2, that's negative 4a, leading us with a equals negative 2 over negative 4, and therefore we have a equals 1/2. Okay. For the value of b, if we let x equals negative 2, again, replacing all x's here by negative 2, we have these equations. And notice that since this is negative 2 plus 2 will become 0. Okay, all this term will become 0. Also, this term will become 0. So that is left for us to look for b, which is negative 2, that's negative 4, times negative 2, that's 8. So we have this equation. So negative 2 on the right side, on the left side, and 8b on the right side. So we have b equals negative 2 over 8, and that led us to b equals negative 1/4. Okay, next. If we let x to be equal to 2, again, replace every x here by 2. So we have this equation. And this time, this term will become 0. Also, this term will become 0. And that is left for us with 2 squared plus 2 times 2 minus 2. So this is 4. This is also 4. That's 8 minus 2. That's 6. And then the right side, this is 2 plus 2 is 4 times 2. That's 8c. So you have 6 equals 8c. And dividing both sides of the equation by 8, we have 6 over 8, and therefore C equals 3/4. So we now have the values of A, B, and C, which are equal to 1/2, negative 1/4, and 3/4. Therefore, we can now write the integral of x squared plus 2x minus 2 all over x cubed minus 4x dx as the integral of the sum of A over x plus B over x plus 2 plus C over x minus 2 dx, which is equal to this integral, and this is what we showed you earlier, and that is equal to 1/2 ln x minus 1/4 ln x plus 2 plus 3/4 ln x minus 2 plus c. So this example allow us to use the case number 1, the non-repeated linear factor. Okay, let's have another example. Say we want to evaluate the integral of x cubed plus x plus 2 all over x times the quantity x squared plus 1 raised to the second power. Okay, we check out the degrees of the numerator and denominator. The degree of p of x, x cubed plus x plus 2 is 3. And the degree of the denominator is 2 times 2, that's 4, plus 1, so that's 5. So meaning the degree of the numerator is less than the degree of the denominator, which is a proper fraction. And since both the numerator and denominator do not have any common factor, then the fraction is irreducible. And that allows us to decompose x cubed plus x plus 2 all over x times the quantity x squared plus 1 raised to the second power into partial fractions. Okay, we take note of the factors of the denominator. You have x, that's linear, non-repeated. You have x squared plus 1, that's quadratic, and repeated twice. Okay. For the first linear factor, we associate a partial fraction equal to a over x. And then for the second factor, which is quadratic, we associate a partial fraction equal to capital Bx plus c all over x squared plus 1. And since it is repeated twice, we have dx plus e all over quantity x squared plus 1 to the second power. So again, the degree of the denominator is equal to 5. That is the reason why we have 1, 2, 3, 4, 5 variables to solve. And since the factors of the denominator is 3, so you have 1, 2, 3 terms to consider. Okay, and then we follow the same step. We write the right side of the equation as single fraction by getting the LCD. You have x times the quantity x squared plus 1 to the second power. LCD divided by x multiplied by a led us to a times the quantity x squared plus 1 to the second power. Then the LCD divided by x squared plus 1 times bx plus c, then that led us to the quantity bx plus c times x squared plus 1. And the LCD divided by x squared plus 1 to the second power times dx plus e, that leads us to dx plus e times x. And since again, the denominators are equal, you can now drop it off, and that led us to this equation. Okay. So in this case, we can now apply simplifying these fractions. Okay, sorry. Simplifying this equation, we have, okay, x squared plus 1 to the second power is equal to x to the 4 plus 2x squared plus 1 multiplied by a. And then you have x times the quantity x squared plus 1 is equal to x cubed plus x. Then we will need to multiply it to bx plus c. And then that led us to ax squared plus 2ax. Sorry, that's ax to the 4 plus 2ax squared plus a. And then plus this 2 by using the FOIL method, bx to the 4. Bx times x cubed, that's bx to the 4. Bx times x, that's bx squared. Then c times x cubed, that's cx cubed. And then c times x, that's cx. And for dx plus e times x, that is equal to dx squared plus ex. So this time, we can now use a technique called equating coefficient with like power. So here, we only consider, we collect similar terms, that is those terms containing the same powers of the variable x. Okay, so we write it again here, and then we equate coefficient with like powers. For x to the 4, you notice on the left side there is no term containing x to the 4, so we have on the left side equal to 0, and then on the right side that's a x to the 4, so we have a here, and then another one is bx to the 4, so we have b here. Okay, and that we let it to be equation 1. And then for the term containing x cubed, since we have 1x cubed on the left side, so we have 1. And then on the right side, we only have this term, cx cubed, so we have c. And then for x, we let it to be equation 2. And then for x squared, on the left side, there's no term containing x squared. Okay, and then on the right side, you have 2a plus b x squared plus dx squared. So the coefficients are 0 equals 2a plus b plus t. And then for the term containing x, so we have 1 on the left, and then another one is on the right side, we have c and e. Okay, and then for the constant term, 2 on the left side, and only this term is considered constant. So you have 2 equals a. And then what we need to look for is to solve this system of equations. So we have to substitute a equals 2 to equation 1, then b is obtained. If we replace c equals 1 to equation 4, then we can look for e. And then we have 0 equals a plus b from equation 1. And then we replace a by 2, so you have b equals negative 2. And then you have 1 equals c plus e from equation 4. And then c is replaced by 1, so you have 1 equals 1 plus e, so e equals 0. And the next thing to do is to substitute a equals 2 and b equals negative 2 to equation number 3. We have 0 equals 2a plus b plus d, and then a is equal to 2 and b is negative 2. Solving this equation, you have d equals negative 2. So with the values of a is 2, b is negative 2, c is 1, d is negative 2, and e is equal to 0. And these values will be replaced to the given partial fractions. Okay? So you have the integral of x cubed plus x plus 2 all over x times the quantity x squared plus 1 squared dx is equal to the integral of a all over x plus bx plus c all over x squared plus 1 plus dx plus e all over the quantity x squared plus 1 square dx. So we'll now replace a, b, c by these values which we have obtained earlier. So we have the integral of 2 over x, b is negative 2x plus c, which is 1, all over x squared plus 1, plus dx, d is negative 2, negative 2x, so plus e, which is equal to 0. So we have the integral of 2 over x plus negative 2x plus 1 all over x squared plus 1, and then plus negative 2x all over x squared plus 1 to the second power dx. So integrating, we can write it as a sum of these integrals. Okay, so you have integral of 2 over x is equal to 2 integral of dx over x, and this term can be decomposed into this fraction. So you have negative 2x dx all over x squared plus 1 plus that one is dx all over x squared plus 1. And then finally, we have minus the integral of 2x dx all over x squared plus 1 to the second power. So as you can notice here, we can now easily identify a straightforward formula to find the integrals of these fractions. Okay, so we now have 2 integral of dx over x is 2 ln x, and then if we let this to be your u, x squared plus 1, your du is 2x dx, and this leads us to negative ln x squared plus 1. And we all know that this one follows an arctangent. So you have plus arctangent of x. And again, this term can be integrated by applying the power formula. Okay, and that led us to 1 all over x squared plus 1. And then you can now add c. So which means the integral of x cubed plus x plus 2 all over the quantity x times x squared plus 2 to the second power is just equal to 2 ln x minus ln x squared plus 1 plus arc tangent of x plus 1 over x squared plus 1 plus c. So what did you notice is that a complicated fractions which cannot be integrated by applying a basic integration formulas is simplified by applying a partial fraction decomposition. So that's it for now, and